welcome to my master thesis. I investigated the vertical farming of wheat in Denmark, and I used the life cycle assessment framework. And I know some of you don't know what the life cycle assessment framework is, so I'll just present it briefly. It's short for LCA, and it's a tool to evaluate the environmental performance of a process, or product, or system. It's also used to compare either processes, products, or system with the same outputs. To make sure that what you're doing is actually an LCA, you have to follow some standards. These are called the ISO standards. And luckily, there are some guidelines or handbooks that make sure that you follow them step by step in the right order and make sure that what you are doing are actually an LCA. The whole process is a dynamic process, meaning that it is relying on interpretations. So throughout the stage of the life cycle analysis, you can go back and forth depending on how one stage influences the other. And also, it's highly reliant on iterations, meaning that even though you present results, you can always do another iteration where you maybe improve some of the data, you gather more primary data, you reduce uncertainty, and that can help the results, especially when you do a comparative study. Then you can emphasize the comparison. So moving on to SEA. What is that? That is controlled agriculture. And it is everything from a greenhouse where you just monitor some of the processes or control some of the processes, like watering or irrigation, to some systems where you control everything, meaning the lighting, the pest control, the irrigation, the climate, the nutrients. Everything is under control, and most of these systems has automated processes. The vertical aspect comes into play when you start to stack these things. Since you have systems, you don't rely on sun. Then all of a sudden, to reduce land use, you can start to stack them on top of each other. And in these systems, you typically find something like leafy greens or herbs, as these have the most success in these systems. And that's something I'll talk more about later. The system under investigation are the indoor vertical farming of wheat using hydroponics, but with soil as medium. Typically, hydroponics, the definition is soil-free farming, but for the sake of this system and the model, I used soil as medium, so I don't add any nutrients throughout the processes. But typically, you would use something like coconut fiber or lava rocks, something that can hold the crop, and then you just add nutrients through water. So why look at wheat? Well, wheat is one of the most important crops in the world. It accounts for a lot of the human consumption in terms of calorie, but it also faces some issues and challenges. It was found in a study last year that there's actually a stagnation in the yield after the 2000s, and this combined with still increasing production indicated that there's actually a decline in the yield. And this was due to climate change, and more specific to extreme weather, meaning even though that wheat is a very resilient crop, in extreme conditions, heavy rainfall, drought, erosion, all the things that follow, it can affect the yield greatly negatively. So here in Denmark, we also are very happy cultivating wheat. Actually, about 8.5% of the total area is cultivated with wheat annually, each season, and that's a lot. And also, I couldn't find any environmental performance of wheat in vertical farming, so that's why I investigated. So, yeah, why vertical farming? All these issues and problems that that conventional farming wheat has, all these uncontrollable factors are actually countered by moving it indoor, and then you control these factors, and that can secure the supply of wheat. And also, since you can control everything and you know how wheat reacts to the best conditions, then you can tweak these inputs and make sure that you reach the maximum yield potential every time you have harvests. And also, since you're not relying on the climatic seasons like we are here in Denmark, you can have still have harvests during the winter when there's no really sun and the conditions are not right for wheat outdoor. Yeah, and as again, since you have multiple harvests a year, to produce the same amount, you actually requires less space. Since you only have one harvest a year outside, you can have multiple inside, and then you can reduce the area accordingly. And the same when you go vertical. And then, more exciting, you can start focusing on new properties. We cultivate wheat in a direction that is, it needs to be robust, it needs to be resilient, it needs to withstand all these climatic, uncontrollable factors, so we don't disturb the yield. And now, since that's not an issue in this system, we can start focusing on something like taste, like texture. We can start targeting what we want with the wheat, which sector needs it, and yeah, it opens up a variety of options in that regard. So that was a little bit about the background, and now we move on to the first steps in the LCA, which is the goal and the scope. So starting with the goal is actually what do we want to do with this study? And what I want to do is evaluate 2 agricultural systems, one vertical and the current practice, which is the conventional. And that makes this a comparative LCA. The method I use is that of environmental footprint, EF for short, 3.0, and that includes 16 different impact categories, which are measurement points. I included 7 here, as they are assumed to be the most influencing impact categories in respect to agriculture. By definition and following the ISO standards, this is a situation A, microscale, and that has something to do with the decision context, as this is not affecting the current way of producing wheat, not right now at least. It doesn't really influence, the result doesn't really influence that. And also we use system expansion to handle multifunctionalities according to the ISO standards. So overall, the goal is to broaden the knowledge base in regard to this topic. And of course, to see which of the 2 systems comes on top in respect to the market. So moving on to the scope, as the goal is what we want to do, this is how we do it. The scope is to make sure that someone else can replicate the whole thing, so it needs to be very transparent and show what how I did this. So the functional unit for these systems are to produce 1,000 kilograms of wheat grain in Denmark, and the functional unit is used to the 2 systems to each other to make for a fair comparison. And to go with the functional unit, we have the reference flow. The reference flow is also to normalize the systems to each other, but also within the system. And meaning that you want a process that is just enough to fulfill the functional unit, not more, not less. And that's what this is used for. And here I used the ground area needed, because they're different for both systems, because it's not the growth area, it's the ground area. And then how long it takes for one cycle of harvest. For the data, we have some requirements. For the temporal aspect, we are in current time in 2021. For the geographical, we are in Denmark, and the technology we use state of the art, and that should be reflected on the processes chosen throughout the model. So that leads us to the actual model. And here we can see that I have some background processes. Here divided into resource inputs and process inputs. The green ones are only applied for the vertical system, whereas the blue is also only applied for the conventional system, and the rest are shared. So all the resource and process inputs are fed into the foreground systems, which is divided into 3 stages. And these 3 stages are assumed to be enough to produce the functional unit that I'm after. Beside that, it's also producing some emissions that we need to account for in the model. And having the preparation, growth, and harvest and ends at the harvest, it makes this system a cradle-to-gate system and does not look into the waste handling and or how the product is being used. So, having defined the goal and the scope, we can move on to the next step in the LCA, which is the inventory analysis. And here we have some of the assumptions. It's the main assumptions for both systems, where we have something about transport, but also we have the byproduct, and this is referring to the straw production. It's not included as it would. It is assumed to be both for the same for both systems, so it doesn't really add anything of value. And also, it is typical for agricultural systems to stop at the harvesting, since it's that you want to investigate. And starting to take the straw and crediting it, it would kind of break the system boundaries, and that's not meant to be. And also the same yield is assumed for both systems per growth area, meaning that the vertical farm is not more dense in the wheat than the conventional. It's the same. Specific for the vertical farm, we have 20 hours of lighting a day. Actually, it's known that wheat can grow 24 hours a day, but past 20 hours mark, the growth is diminished. So I took the values for the 20 hours a day. We have 5 harvests a year, meaning that we have a 70 days per cycle, so you can harvest. I decided to add the 5 floors because I assumed it wouldn't add a lot of the modifications to a structure. You can put it into a normal warehouse or barn. In my case, a steel construction. And also, since all of the processes are indoor and controlled, and you have all the water filtering systems and the air filtering systems, I reduced the emissions from the nutrients out of the fertilizers by 70%. And specific for the conventional system, we have that the soil is supplying all the micronutrients. So it's only the macronutrients you need to add. And we're relying on rain, so no additional watering. The farm is also some transportation assumptions. And then, more importantly, the variation in yield size is not reflected in the study. It's in Denmark, it's in one season, but the variety in yield size may vary from place in Denmark to another, depending on the soil quality, depending on the rainfall, the drought, and so forth. This is not reflected. This is the average yield size. So, moving on to the actual data collection. It's important to know which process or what processes is important for producing wheat. And here you can see that even if you don't know all the factors, then all of a sudden you can have a reduced yield in wheat. So having a limiting factor you don't know is a bad thing. It's important to all the processes you need. Otherwise, you don't really reflect reality. So I've divided it into data types. I have the energy, which is all the electricity consumption. I have the active material, which is the material being consumed by the process or transformed by it. Then I have the passive material, which is being reused for each harvest. And then I have average data. It is divided into life stages, as I presented before, and also which system belongs to which process. But I cannot just say, this is the number I need here. I need to do some data quality assessment and determine the data uncertainty. Here I use the pedigree matrix, which is a semi-quantifying uncertainty tool. Here I take each process and I evaluate it out of some indicators and score it from 1 being the best to 5 being the worst. And also taking into consideration each process having the worst score. Putting that into the equation here, you can see that I get a number. You cannot see it here, but I get a number. And based on the number, I can do what is called a data quality level, which is more like trying to do a qualify statement of the data uncertainty. And I did that, and here you can see it for each life stage. Here is for the vertical farm and the conventional farm. As I said, close to 5 is worst, close to 1 is best. And not surprisingly, the vertical farm is performing quite poorly in terms of uncertainty. There's a lot of uncertainty. And using the processes, I mean, there's not really a process that said, yeah, this is how you do vertical farming of wheat. So there will be some mismatch across the indicators. And that is also what is reflected here. For the conventional, it's better, meaning there's less uncertainty. So it should be, as we have a lot of good quality data regarding conventional farming of wheat. The mismatch is maybe is because some of the processes is not located maybe in Denmark, or the time scale is a bit off, and that affects and adds uncertainty when you want to replicate the study here in Denmark. And this is the study, and I listed that I said the requirements before. So yeah, we need to consider this when we interpret the results, because adding uncertainty, yeah, it is uncertain. So moving on from the inventory, we can go to the next step in LCA, which is the impact assessment. So in the impact assessment, we start to get some results. And this is presented in the 7 impact categories. And I would lie if I wouldn't say I was a bit disappointed of how poorly the vertical farm system worked. I needed to check the numbers again and again. And yeah, it was like this. And especially in the land use, you can see it's a factual difference. You can see it's quite significant. So that was how the system was modeled and how it looked. But why does it look like this? I started by doing a hotspot analysis, trying to see which of the life stages was responsible. And here you can see that, yeah, the difference is in the growth phase by far. Even the harvest phase has 3 impact categories that actually was better than the conventional. But I needed to go further because this didn't tell me much. So I did another kind of hotspot analysis called a process contribution, where I looked within each impact category for both systems and saw the 3 most contributing processes. Here you can see that for the vertical system, the lighting process is by far the most dominated. It's above 90% in all impact categories and almost 100 in some. For the conventional system, it was the fertilizers that were the most contributing process in all but 1 impact category, but it was present in all of them. And both of these are linked to the limiting factors of producing wheat. But it's to look a bit further, as lighting was the main to blame why my system was looking like it did. So I looked into the unit processes, or the sub-processes of the lighting process. It was connected to electricity consumption in this process. And what I found was that it was all the fossil electricity generating technologies that were to blame. It was the same across all impact categories. It was the coal production, it was oil, it was the natural gas, and it was also wood chips used in providing a power plant. And that actually explains why the land use was so different, because wood chips require some woods and trees, and these trees were has to come from somewhere, and they take up space. And for that, it was forestry that was the most dominating there. So moving on to the final step of the LCA, which is the interpretation. It is not only relying on the impact assessment. And as I started saying, this is a dynamic process depending on the interpretation. So it actually also includes data from the other steps of the life cycle. But it can also affect the other steps. So it is really a dynamic process that you can go back and forth many times and spend a lot of time on it. So diving into the interpretation, first I needed to make sure that my numbers were real. I need to make sure that I could use them. So first I did a robustness check on the method. And as I said, I used the EF 3.0. So I did a test against the more commonly used, maybe the recipe. And these are the normalized results from both of them combined. And here you can see that for the climate change impact category, it was almost the same. There was no real difference. And yeah, for the eco-toxicity, there's a big difference. It really determines when do you think too much is too much. But I said, okay, the climate change, it seems to be within beyond the method that I use, so I can compare it across methods. Since I have seen no other results for the vertical farm, I took the results from the conventional farm within this climate change impact category that is now beyond the comparison with methods. And I did a reality check. My system said that about 0.5 kilo of CO2 produced, kilo reproduced, was the load in this impact category. So I checked with the big climate database and CISA, and it agreed with my findings when I just looked at those life stages that I included here. And also a study conducted by Lisbeth Mogensen had the same values. So this made sure that my results were in the right order of magnitudes when compared to the reality. Also making sure that my assumptions were somewhat accurate. I needed to make sure I test for some other kind of uncertainty. This is the sensitivity. And this means if I check if a process is sensitive to uncertainty. So here I looked at the most contributing processes for each system, and I increased the value of within the process by 10%. And then the change in result that gave I compared to the original baseline system. And if the change was greater than 5%, I would say, okay, this process is sensitive to uncertainty for that impact category. And for the vertical system, you can see that it's all sensitive for the lighting process. And for the conventional system, 5 out of 7 impact categories are sensitive for the fertilizer. And what this tells us is really more uncertainty, and more uncertainty for the vertical farm, as this is also the most contributing process. Keeping in that lane, we will talk a bit more about the electricity. I modeled my system on numbers based on the Danish Department of Energy for 2021. You can see the development and the projection towards 2030 in the same department. Here, there are more technologies. Here I listed the most contributing to make sure that you could read the chart. You can see that offshore wind and onshore wind and solar power is something that you will focus on for the future as these sectors are increasing. But also coal, natural gas, and oil. You can see the contribution to the total electricity mix is quite small, but it was a big deal when looking at the process contribution for the lighting process. So even though it's a little part of the electricity mix, it contributes a lot in respect to the environment. So with these numbers, I did some scenarios. I did a scenario, a future scenario, up until 2030, where I changed the mix to match the numbers I got from the Danish Department of Energy, and also found the projected efficiency of the LED used in the system. So, and that was about 100% increase in efficiency. And these are the results in all impact categories. As you can see, it's an improvement, luckily. So if you just wait until 2030, this is sort of more or less what it should be. We focus on the energy of wind power, offshore and onshore, and the solar. I wanted to see how these performs against the baseline vertical system if it's only powered by either of them. And it can be seen that across all energy technologies, they outperform the baseline system. And especially true for the onshore wind energy generation. So I used the data that I gathered from my scenario analysis, and I did a new scenario called the best case scenario. Presented here, you can see numbers that you've already seen, the factual difference between the conventional and the vertical. Those are the two main, the baseline systems. And then you can see the difference of the best case scenario compared to the conventional system. And just by looking at the numbers, you can see it's a big improvement, but it's not better than a conventional system. And these numbers needs to be taken into consideration with all the uncertainty that I added in the model, because these are just the average numbers that I gave. I couldn't get an interval. An interval would help determine the uncertainty. So maybe if the interval was large enough and included the value that is actually presented in the conventional system, then I would have a portion of trials, what do you call it, where the best case scenario would actually be better than conventional, and that would be something you could pursue and work with. So these are just the average number, and it's difficult to say with the significant difference that it is better, it is worse. You need to look into the uncertainty of those. But it's an improvement when you do the best case. So I wanted to make sure or investigate why are these numbers looking like they are. So I looked up in the FREDA food database in DTU and compared it with lettuce, which is widely used in vertical farming, and found that the wheat requires 25 times the energy of lettuce. So that started to make sense. And also, if we were to take all the production of wheat in Denmark and move it indoor with the system I modeled, it would require about 14% of the total Danish energy consumption. So with those words, we'll get to the very last bit, which is my conclusion. So it is not really environmentally feasible yet, at least not with what I investigated here. And of course, it was due to the electricity being the main barrier. But there's also some recommendations. So of course, we need to make sure that the uncertainty is quantified so we can work with it. We also need to reduce the uncertainty a bit. By quantifying the uncertainty, we could do things like run a Monte Carlo simulation, where we could overlap the system and see if there's an overlap with all the uncertainty that the system has, and that would be interesting to see how many times the vertical system would beat the conventional. But reduce uncertainty. It could be done by getting better primal data, by coupling an LCA with an experiment under the conditions that you want to investigate, that you think can represent reality, and then you can get all the data, less uncertainty, more primary data, and that would definitely help also to emphasize the real relation and difference between the two systems. Other than that, it would be interesting to look at different systems. I modeled with 5 floors, but found that the electricity was the main barrier. And if you make sort of a hybrid system with that keeping in mind, you could make a glass roof and use it on the ground or on the ground without levels. And then you could get all the benefits of the indoor farm, but also utilize the sun's energy, which would greatly improve the system in respect to the environment. It would be interesting to see how that compares, at least. So that was it for me. I'm not sure what the time says. I think it's okay.